In this video, I'll do a couple more examples of functions that are built as a combination of various types. So there is an overarching principle that we are kind of applying here, and it was applied in the previous video, but I didn't really make it clear there, and so I wanted to make it more clear here. The idea is if you have a function which has multiple pieces, all of the pieces have to be well defined in order for the function to be well defined. If one piece breaks down, the whole function breaks down. And so as you'll see, the idea of intersections of sets plays a big role when you're finding the domain of some function which is built from several different kinds of pieces. Let's take a look at these examples here. Now before we get started, let's be clear on what an intersection is. Here's a picture that shows what it looks like when you have two sets that intersect. And so the red shaded portion is where the intersection is. And there's a definition too. If something is going to be in the intersection of two sets, then it has to be in both of the sets. And if it's not, then it's not in the intersection. So to see if you're tracking me here, I have an example down at the bottom that shows the intersection of two intervals. Why don't you pause the video and see if you can write the intersection of that of those two intervals as a single interval using interval notation, and maybe make a number line picture, something like that. Go ahead and pause it, see if you match. So you can see I've got a crude picture down here at the bottom that shows both of these intervals on a number line. And so the interval from -infinity to +3 with the square bracket is shown in blue. And you notice that the endpoint is solid because the 3 is included in the set. And the interval from -2 to 5 is shown in green. And the endpoints are open because neither -2 nor 5 is included in the set. So clearly, if we take the intersection of those two intervals, we're going to get everything in between -2 and +3, as you can see shaded in red there. But what about the endpoints? Well, if you follow the definition, you understand that the interval in green does not contain -2. And since it's not contained, it can't be in the intersection. However, because the set in blue contains +3, as does the set in green, 3 is included in the intersection. And so if you were to write the intersection using interval notation, it would look like this. And so it's the half-open interval from -2 to 3 with a square bracket on 3. Now let's go to the examples on the slide. First up, I'm going to do the first function. F of x is x over the root of x minus 3. Now as you'll see, we have two conditions that have to be satisfied here. We need the radicand of that denominator radical, x minus 3, to be non-negative. And we also need to make sure that the denominator is not 0 because it's a denominator. And so let's take a look. So I've jotted down my two conditions. And if you know what you're doing, I don't know that you necessarily have to write every single one, but for these examples we want to be as clear as possible. So we're going to showcase every little detail. So as far as x minus 3 greater than or equal to 0, that's pretty straightforward. All you have to do is add 3 to both sides, and you get as follows. And for having the radical being non-zero, that's pretty good too, because really all you have to do is notice that the radical is going to be 0 when the radicand is 0. In other words, when x is equal to 3. So we have two conditions here, x greater than or equal to 3 and x not equal to 3. And if we intersect those two conditions, we get x greater than 3. And so that happens to be the domain of this function. So if we state it in set builder notation, we have x such that x is greater than 3. If we put it in interval notation, it's the open interval from 3 to +infinity, round parenthesis on both ends. Let's look at the next example. For the next function, g of x equals the square root of quantity x over x plus 2, you can see just by inspection what the conditions are going to be. First, we need that radicand, x over x plus 2. We need that to be non-negative. And we also need the denominator of that not to be 0. So we need to have x plus 2 not being 0. And of course that means x can't be negative 2. So let's put those down and we'll see about what we need. It's the first condition here that's going to take some work. The second condition is very straightforward, x not equal to negative 2. So keep that in the back of your mind. Let's go about analyzing x over x plus 2 to see where that's going to be non-negative. So here's my sign diagram. And if you're wondering about the numbers down at the bottom, when you do a sign diagram like this for a rational expression, you put the numerator and denominator roots onto the number line proxy down there at the bottom. So negative 2, as you know, is a denominator root, and 0 is a numerator root. And in this case, negative 2 is wearing an open circle because it's a denominator root. We can't have that. And 0 is wearing a closed circle because it's okay if a numerator root is 0. And in this case, the inequality is greater than or equal to 0. And so if the function or the expression x over x plus 2 is 0, we're okay with that. Now let's look at the first of the quantities, x. X is an increasing linear function, has a slope of 1 and a y-intercept of 0. It crosses the x-axis at 0. And when you're to the left of 0, you can look at the graph and you can verify this yourself. We're in negative territory, and when we go on the other side of 0, on the right side, we're positive. And so again, this function is negative when you're left of 0 and positive when you're right of 0. Okay. As far as x plus 2 is concerned, again, an increasing linear function, slope of 1, y-intercept of 2. You can look at the graph for yourself. It crosses the x-axis at negative 2. And when you're to the left of that root, it's negative. When you're to the right, it's positive. And so if you fill out your sign diagram, here's what you got. And so if you have two negative quantities and you divide them, you get a positive result. If you have a negative and a positive in any order, you get a negative result. And if you have two positive quantities, you get a positive result. And so we're looking for where we are non-negative, positive, and that would be these two regions right here. And so we want to now consider, okay, how is that going to mesh with what we had said previously? And if you want, you can look at the graph of this and you can see that it is saying the same thing. I mean, it's a little bit easier to understand what you see with the graph after you've done the analysis. But anyway, here's the graph of this function, just for your interest. I'll just graph it. It was x divided by the quantity x plus 2. And I think a standard zoom would be good. And so you can see the graph right there. So this half over here is positive for all values of x, and we found that. And then this piece right here only becomes positive when you cross the origin right there. And so we found that as well. Anyway, let's take a look at the answer to the problem that we're actually looking at. So if you recall, we said that we had two conditions we need to satisfy. One of them is we cannot have x being negative 2 because that makes the rational expression undefined. And we're finding that we need to have the shaded region is where this argument, this radicand, is going to be non-negative. And so it happens that this does not include negative 2, and that's good for us because that was one of the things we needed. And so the set that you see here is going to be the domain of the function. So if we state the domain using interval notation, it would be as you see, and it can also be stated using set builder notation, whatever seems good to you, whatever the question is calling for. Let's look at our last example. The last function, h of x, is a combination of two separate radical functions. And so again, we want to make sure that all of the pieces are well defined, and when we take the intersection of all those constraints, then we have the domain of the function. Let's take a look. So the first piece that we're looking at here is root x. Where is that going to be well defined? Well, we want the radicand to be non-negative, and the radicand is x, and so from the first piece, the first condition we get would be as follows. We want x to be greater than or equal to 0. For the second piece, the radical 4 minus x, we want the radicand to be non-negative. And so we want the quantity 4 minus x to be greater than or equal to 0. And so saying that we want 4 minus x to be greater than or equal to 0 is the same as saying that we want 4 to be greater than or equal to x. Now, as an aside, that inequality, 4 greater than or equal to x, it's perfectly sensible if you understand how to read inequalities. But you know what I've found over the years is that a lot of people will get it backwards because they're uncomfortable having the variable on the right-hand side. In other words, they prefer inequalities like the one you see given as condition number 1, where the variable's on the left. And so you can translate this inequality. It's not a problem. You just have to pay attention when you're doing it. It is the same as x less than or equal to 4. So as you can see from the drawing that I've made down at the bottom, we're intersecting those two intervals. And obviously the intersection, the overlap, is going to be between 0 and 4. What about the endpoints? Well, again, the definition says that something has to be contained by both sets in order to be in the intersection. And so if I'm looking at the value of 0, 0 is contained by the first set, which is in blue, x greater than or equal to 0, and it's also contained by the green set, because 0 is less than or equal to 4. And so 0 is in, and likewise 4 is in. And so in interval notation, the domain for this function would be the interval from 0 to 4 with square brackets on both ends. A little bit sloppy down there, sorry about that. But anyway, I hope that this has been helpful, and if you have any questions, as always, drop me a line. Otherwise, go on to the next video.